Thank you, Richard. Fred Skiff, professor of physics from the University of Iowa, will be sharing this first session with me, and I have quite a bit of material to cover. But I'd also like to leave time for discussion, which I think is important. And so I'm going to be omitting one section of my outline, section 4. There's another reason for that, and that is that some of the material that I would have covered in that section has yet to be published. It will appear later this year from Tim and Lydia McGrew at the University of Western Michigan. I recommend to you, though, this book by Del Ratch, which is an alternative approach to inferring design. That is an alternative to Bill Dembski's approach, which I'll be discussing today. So I'm going to try to end at 11 and then have some discussion following that before turning the floor over to Fred. My title today is The Basic Logic of Intelligent Design Reasoning. And this notion of intelligent design is increasingly debated, especially in the United States, but also now internationally. Last year in Germany, a biologist, a plant biologist, lost his web page because he had links on the web page to, he was at the Max Planck Institute, he had links on the page to intelligent design sites, and his superiors at the Institute made him take those down and put them on a personal, private web page. And this was actually written up in Nature as a controversy. So it's not just in the United States that this notion is generating controversy, but also now internationally, as I mentioned, here in Europe. And there's been a tremendous wave of publication in the area. This is a new book that will be out shortly from Cambridge University Press, entitled Debating Design from Darwin to DNA, edited by my colleague at Discovery, Bill Dembski, and also Michael Ruse, who's a Darwinian philosopher of science at Florida State University. This is a very interesting book. It's a four-way conversation about this question of intelligent design. The four positions represented are, of course, design, but also classical neo-Darwinism, self-organization theory, and theistic evolution. And under each of those four positions, there are several chapters by different authors talking, if you will, in a four-way dialectic about this question of design. Now, Cambridge, major university press, took on this project because they saw its increasing relevance to the interaction of science and culture. I'll just mention a few other books that are noteworthy. This book appeared in 2002 by two historians looking at the question in the United States, but it's also relevant internationally, of our culture's search for a creation story. This is another History of Intelligent Design, an excellent one that just won an award from Christianity Today magazine. The chapter that you have reproduced in your binder is taken from this book by Larry Witham, who is a journalist who covers science, has published articles in Nature and Scientific American. And then Oxford, 2 years ago, brought out another history, also by Larry, dealing with the more general question of the creation-evolution debate. Now, this is just a small sample of a very wide range of books that have come out recently on intelligent design. So the controversy is really brewing. Now, detecting intelligent causes is a central aspect of human rationality. And for our discussion this morning, we'll look at two main problem areas. The first is epistemology. How do we know? How do you know that your wife loves you? How do you know that you've paid your electrical bill, and so forth? How do we know, in particular, when a mind like our own has acted in the universe? This is a question of the epistemology of science. How do we know? Secondly, a question, in fact, I think really the deepest question we'll deal with today is the definition of scientific knowledge itself. What counts as scientific knowledge? In particular, can one use intelligent causes in scientific explanation? How are we going to answer that question? And the main problem we'll confront is this. Right now, in 2004, there are very widely accepted definitions of both the epistemology and structure of scientific knowledge that I'll argue may be seriously hindering or limiting our ability, the ability of the scientific community, to detect the action of intelligence in the universe. And this is the philosophy of science that has this effect. It's come to have a name called the rule of methodological naturalism. Now, as expressed very succinctly by the National Academy of Sciences in 1998, that rule says that the statements of science must invoke only natural things and processes. Now, this adjective, natural, will be something we'll want to come back to later in the talk and also in our discussion, because I think it's very problematic. But I want you to note the logical structure of this rule. This verb is an imperative. I have two daughters, 10 and 12, and when their rooms are untidy, I tell them they must clean them. They don't have a choice. It's an imperative. That's what they must do. And this rule not only has this imperative here, you must do it, but then there's the logical modifier only here, asserting that all that resides in the toolkit of science, when we come to explain a puzzle in the world, are natural things and processes. Now, the question we want to ask is, A, is this true? And B, is it a good rule? We'll come back to that. Now, I want to run through some examples of detecting the action of intelligence. This is something you do on a daily basis, and you're not probably ever consciously aware that you're doing so, unless you're confronted with some real complex puzzle. But underlying or undergirding what you do is a method, is a logic. A couple of examples. This is the front page of the Los Angeles Times just over a year ago. This is published March 31st, 2003. Now, this photograph appeared not just in the Los Angeles Times, but in other papers throughout the United States. It purports to depict a British trooper here outside Basra telling this Iraqi person with his child to stay down because mortar fire is coming into the area. Now, a few days after this photograph was published, the photographer was fired by the Los Angeles Times. So see if you can figure out why. Here's the picture. Now, suppose you're a reader of the LA Times and you go out and pick up the newspaper in your driveway and glance at it on that morning of March 31st. You might not notice anything unusual about this photograph, but look at the left-hand portion of the picture over here. Notice, for instance, this gentleman, the curve of his back here and the curve of his leg, and then look at this figure here. Or look at this profile, and it's a little hard to see, but that profile. Or especially this profile and that profile. There are an unusual number of identical twins in the left-hand portion of this photograph. And the reason they're there is not because this picture actually ever occurred as a real event, that is, photons entering the lens of a digital camera. What actually occurred was this. The photographer took this picture and this picture, and then he looked at them, and he realized that he could possibly win a Pulitzer Prize for journalism, for photography, if he combined this image, which is more dramatic than that, with this image, which is more dramatic than that, and that's exactly what he did. He photoshopped them together into this, which then got the best spot you can have in a newspaper, the front page above the fold. That's the first thing your eye sees as a reader when you open a newspaper. His editors agreed with him. They put the picture there, and unfortunately, it was a fake. It didn't exist. Now, you're a reader of the Times, or you're his editor, and when you look at the accounts of what happened when this was discovered, his editors were just heartsick, and they immediately began to look for some natural explanation for why this should have happened, some computer glitch, some error in transmission from Iraq to Los Angeles. They immediately began to look for a natural cause for that pattern. Of course, there was none. The reason that pattern, that photograph existed is because the photographer meant it to. So they went into their toolkit and asked, is there a natural cause, or is there an intelligent cause for this pattern? Of course, there was no natural cause. and he had violated the editorial policies of the newspaper that they would not publish electronically manipulated images, and of course he was fired. We can think about it this way. Here's our effect, our real pattern in the world that we wish to explain, and we have a range of possible causes for that. There's a possible natural cause or a range of possible natural causes, and then there's an intelligent cause. Of course, there is no intelligent cause, and any rational person, irrespective of their philosophy, is going to ascribe that pattern to an intelligent cause. Now, there's another option that we have, and that's to say we don't know. That's to defer explaining this pattern and say we just don't know. Neither of these is adequate as far as we can tell. So we're going to we'll withhold our judgment about the explanation of the origin of this pattern. Of course, we don't do that in a case like this or in other cases that we'll look at. We do, in fact, refer such patterns to intelligent cause uniquely. But later in the talk, we'll come to cases where this is a live option. Now, let's look at the structure, the logical structure of these inferences. There's a causal impotence claim that has the following form. There is no natural, that is non-intentional cause for the appearance of the same persons twice in a single exposure photograph. You can't do it. You could if you did some tricks, I imagine, but that would not be natural or non-intentional. That would involve deliberation. No physical cause can produce the effect or pattern in question. Now, that kind of causal impotence claim is essential to many areas of human inquiry, all types of forensic investigation. The whole genre of the detective novel would be stillborn without our ability to say certain patterns indicate intelligence uniquely. People ordinarily do not splash gasoline or petrol around their living rooms. So if you're a fire investigator and you go to the scene of a fire and you find traces of an accelerant in the carpeting, you have reason to believe the person meant for that building to burn down. So all types of forensic investigation presuppose that we can infer design. Patent and intellectual property law. Years ago, George Harrison, the Beatle, was sued by a songwriter because the melody for My Sweet Lord, Harrison's famous rock tune, My Sweet Lord, was too close statistically to an earlier melody that this other songwriter had copyrighted. And it went to trial, and Harrison ended up having to pay quite a bit of money to this other songwriter because the match was too close for it to have been independent. So we adjudicate claims of intellectual property and priority in terms of, could you, as a creator, have come up with that pattern independently of this other pattern, or did you, in fact, copy it by intent? Being able to make those kinds of judgments depend on being able to detect design. Cryptography and cryptanalysis, code making and code breaking. The code maker wishes to embed a meaningful text in what would otherwise appear to be random noise. Hide it. He wants to hide that meaning and yet have someone at the other end be able to retrieve it. The code breaker wants to sift what appears to be randomness to find those bits of meaning that are residing in it. Again, both of these presuppose this. Detection of fraud in science. In many respects, I think this is the most interesting example of the ones that I'll give here. And I'll give you one sort of mini case study. A very unhappy story, actually, when you look at all the details. Hendrik Schoen was a young physicist in his early 30s at Bell Labs in the United States, and he was on his way to winning a Nobel Prize. He had a string of publications in solid-state physics that were amazing. He had amazing results. And published in very prominent journals, in fact. The problem is no one could replicate them. No one could replicate his results. And even though the results appeared to be astonishing, it was troubling to the rest of the community that they could not replicate Schoen's work. Well, Bell Labs formed an investigative committee, and they discovered that Schoen had faked his results. This is an article from the New York Times describing this. And in early 2000, this story made national and international headlines. Because up until this point, as I indicated, Schoen was on his way to a very distinguished career in science. Here's how they caught him. Here are two figures from two independent, putatively independent experiments published independently. Now, you'll notice that these figures, the lines are identical, even though if you look at the axes of these diagrams, the values are very different. The figures themselves are identical, right down to the random noise. There it is, reproduced so you can see it. These curves are identical. You can superimpose them. And when this was brought to the attention of the investigative committee at Bell Labs, the physicist there said, he faked it. There's no way that two independent experiments could get the same noise in an otherwise random data line unless one of these is a copy of the other. He took the same data and reproduced it in another paper, putatively or supposedly representing an independent experiment. Once that was discovered, all his publications were retracted. He lost his position, and his career went down in flames. We couldn't make this kind of inference. And if you look at other cases where fraud in science is caught, when it's detected, it always presupposes a design inference. Why is there this match? Because Schoen intended there to be. He didn't notice it, but that was his intent. Now again, if you look at the logical structure, there's a causal impotence claim. The investigators said there is no non-intentional explanation for that pattern. No physical or unintelligent cause can produce it. Only from deliberation. Archaeology and paleoanthropology, that's self-evident. A trained archaeologist, if you've ever go with a trained archaeologist out into the field, walking along, and it looks like rubble just scattered on the ground. That person can pick out a pottery shard where you or I might walk right past it. Their detecting apparatus is very finely tuned. Paleoanthropologist who works with early humid prehistoric settlements can point out a hearth, a place where a fire occurred, but that fire was controlled. It had boundaries. There are bits of ash there. There are other indicators that show the deliberate use of fire for some purpose. Again, both of these disciplines depend on being able to make these kinds of inferences. Psychology, of course, is self-evident. Now, we might ask, but of course, Paul, we're only dealing here with human intelligences, members of our species, Homo sapiens. How about non-human intelligence? Now we come, I think, to the most philosophically interesting category, and that is the search for extraterrestrial intelligence. Here's Jill Tarter, astronomer, SETI researcher. Jill Tarter provided the real-life model for the Jodie Foster character in the movie Contact, in the novel based on the novel by Carl Sagan. And she's here. This is my view of the search for extraterrestrial intelligence. Anyway, they're in a computer room in Puerto Rico at the Arecibo telescope, the very large radio telescope built into a natural depression in the mountains of Puerto Rico. She's watching a computer screen, and they're testing a program for detecting designed patterns. I like what she says here. It would be nice if they sent something obvious like the digits of pi. Because they haven't, that guy is rather bored. Just over 10 years ago, Nature published a very interesting paper by the late Carl Sagan and colleagues at Cornell, and I see University of Iowa there, actually, Department of Physics. As the Galileo spacecraft was on its way out into the solar system, it got a gravitational boost from passing by the Earth. And as it did, Sagan and his colleagues said, why don't we do a test run? We'll turn the craft so its instruments face the Earth, and we'll see if we can detect the presence of intelligent life in at least the one instance where we know that it exists. We like to believe that there's intelligent life on Earth anyway. So, as you can see here from their abstract, they say, we did it. the presence of narrow-band, pulsed, amplitude-modulated radio transmissions seems uniquely attributable to intelligence. It's a fascinating paper. I recommend it to you. I'm sorry this didn't reproduce very well, but here's what SETI is hoping to find. This is the screensaver from the SETI at Home program. SETI at Home is a distributed computing project where you can download analytical software and then batches of data from SETI radio telescopes. And when you're not using your computer to run a spreadsheet or write a paper, it's just sitting there, the spreadsheet will, or excuse me, the screensaver will run, and it will be analyzing these radio transmissions. Now, a friend of mine, professor at Northwestern, has this screensaver, and I looked at it at his home, and ordinarily this region here is just bubbling with peaks. It's static. If you listen to it on a speaker, it'd be shh, not very interesting. This, however, in fact, when you go to the SETI at Home project and they say, there's a web page that says, well, what are we looking for? And they reproduce this. It's artificial. They don't actually have this. But this is what they would like. A narrow band. You can see rising and falling here as the telescope swings across the sky. And it's not bubbling with noise. There's a clear, narrow band peak there. That would be the eureka moment, and that's what they, with one or two exceptions, that they were never able to reproduce. That's what they don't have, but that's what they're looking for. Why? Because they argue narrowband transmissions are diagnostically artificial. We know no natural cause that would give that sort of pattern. And again, here's their causal impotence claim. We don't need to spend much time on that, but there's another interesting feature. It wouldn't just be the narrow band. That would get your attention. But Tarter says, what I'm looking for is something like the digits of pi. Something obvious. Well, why would it be obvious? It would be obvious because pi is a mathematical object. The ratio between the circumference of a circle and its diameter. Here are the first 500 digits. Now, as far as we know, mathematical objects like pi are comprehended and produced in our universe only by minds like ours. If pi came in on a carrier frequency, we would have very good reason to believe that there was a mind like ours at the other end of that signal. Undoubtedly not a member of our species. So we would be intersecting analytically with a creature that had a mind, and that's about all we could, a mind capable of grasping mathematical relations, and that's about all we could say about it. And also that species, whatever they are, is able to manipulate the electromagnetic spectrum to do things like carry this pattern. No natural cause, so we have that causal impotence claim, but also Del Ratch, in this wonderful book that I recommend to you, it's very, very insightful, says that these kinds of patterns, mathematical patterns, are mind correlative. They indicate strongly that there's a mind involved, not a natural, strictly natural cause. So why is there this intense controversy about design? Everything I've said so far should be pedestrian to you, should be obvious. Well, the reason design is so controversial is the theory and the research program are widely seen as violating the rule of methodological naturalism. This is not controversial. This part of the definition, that the agency of intelligent causes may be used in scientific explanation. I've just shown you several different types of human inquiry where it's absolutely essential. The controversy arises here. And there may be evidence that such a cause has acted in the history of the universe and Earth's organisms. It's this that makes the scientific community so agitated. So let's look now at methodological naturalism, the rule itself in a little more depth. Now, the first thing we might want to ask about this rule is, in what sense is natural, this adjective, doing work for us analytically? You can think of science as a game with rules. About 20 years ago, when I was an undergraduate studying the philosophy of science, I had lunch with Ron Numbers, who's a prominent historian of science in the United States. He was writing a book, and I had some archival materials that he wanted to see from my grandfather. So he took me to lunch at a little German restaurant near where I lived in Pittsburgh at the time. And we got to talking about this rule of methodological naturalism. And I said to him, Ron, it seems to me very strange that an empirical possibility like design, after all, it could have happened, is excluded from the list of candidates for the origin of life, or for the origin of humankind. It could have happened. Why can't science consider the evidence in light of that possibility? And he was tucking into his Wiener Schnitzel, and he said to me, well, of course it could have happened. That's not the problem. He said, the problem is, Paul, science is rule-governed. And he used an analogy to baseball. Here's our toolkit. And he said to me, well, let me go back a bit. He said, since the 19th century, the toolkit of science has been restricted, since the middle of the 19th century and the rise of Darwinism, the toolkit of science has been restricted to natural causes and intelligent causes where the intelligence is Homo sapiens or animals only, members of terrestrial life. What's not allowed is that. So what methodological naturalism does is provides some analytical cut here between these two types of causes, eliminates these, and that's what's left when you come to explain a puzzle in the universe. And he shrugged. He said, look, so what? Science is a rule-governed game, and just like baseball, you can't hit a foul ball. In baseball, the play of a fair ball is defined by the first base and the third base line from the place where the batter is standing. Actually, in cricket, there are no foul lines. A ball hit in any direction, 360 degrees from the batter, is a fair ball. That's not the case in baseball. You can't hit a foul ball, he said, and run straight to third base. Actually, even if it were a fair ball, you'd have to go to first. So this is really breaking two rules at once. And he said, so what? Science rules out certain kinds of causes. That's just how the game is played right now. Well, what's wrong with that? I want to look at a metaphor from this gentleman, Elliot Sober, who is a philosopher of science at Stanford and the University of Wisconsin, and has, for about the past 10 years, has spent much of his time as a critic of intelligent design. In fact, I was saying to Bill Dembski last year that if Sober publishes anything else on intelligent design, he's going to have to join the Discovery Institute where I work and hang out his shingle as an intelligent design theorist. He writes about it and speaks about it all the time. Now, Sober is a critic of design, but he's also a very good philosopher of science. And he has this wonderful image of looking for causes in science, which is really what I think much of science is all about. If you remember when the SARS epidemic began in the Far East, for a long time, people were very frightened because, or medical scientists were very frightened because people were dying and they didn't know why. Well, when you find the virus that causes SARS, you identify the cause, and then you have some hope of understanding and controlling it. So Sober puts it this way. He says, saying what the cause is like knowing where the treasure is buried. Well, that suggests a model. Here's an island, not a real island, a conceptual island, complete with Microsoft clip art. And this island is where we're going to go looking for the cause of phenomenon or effect X. We want to find its true cause. And that's where we can imagine ourselves landing here, and we're going to explore this space. Now let's suppose the true answer is here, like a treasure map. And the true answer is that life was intelligently caused. We don't know this. We don't have this treasure map. But if we did, that's where the treasure would be buried, and that's where we would want to dig. This is what we know. Nothing. We're beginning an investigation. We're going to look for the true cause of phenomenon X. Now, what does this rule do to that island? Well, what it does is it makes a no-dig zone. Like a no-fly zone. We can't go down there. There's a big barrier here, and this is off limits. Even though the true answer resides there. Methodological naturalism forbids us to dig in that region of the island. And what will happen is this. We will spend our time digging out here fruitlessly because the actual the true answer, the true cause for X, if it was in case of an intelligence, is here. Now, this little metaphor should tell you that there is something profoundly wrong with methodological naturalism as a rule. What if life on Earth were intelligently designed? In other words, that's what really happened. If we're bound by this rule, we as scientists, we could not possibly discover the truth about the history of life. So just from this very simple thought experiment, we should be able to see that there is something very wrong with methodological naturalism as a philosophical framework for science. Now, I want to shift gears, set methodological naturalism aside for a moment, and look at one attempt to understand what it is, understand the underlying logic of design inference, and that is Bill Dembski's notion of the explanatory filter. And this is what philosophers of science call a rational reconstruction of design inferences. What's a rational reconstruction? Well, here's pi, the first 500 digits of pi, a mathematical object produced by and grasped by minds like our own. Here's that narrow band radio transmission pattern that would indicate or at least lead us to suspect intelligence. Here's Schoen's faked data. Here's the diagram. All of these are going to lead us to infer design. So what we're asking for is a general theory that captures all of them, some general theory that will capture all of those disparate kinds of inferences or patterns, and then predict or allow us to capture other patterns that we haven't yet seen or analyzed, such as Poussin's St. John on Patmos, wonderful oil painting in the Chicago Institute of Art, or a Harrier jet, or Drosophila, very interesting, arthropod, or a protein. In other words, we want a general theory, our rational reconstruction of all these kinds of inferences, and these, of course, would be very controversial, that will bring them all together under one general theory. And this is what Dembski is trying to do with his notion of the explanatory filter. It was first laid out in this book, The Design Inference, now 6 years old, published by Cambridge. It's actually the best-selling book in this study, in this series, Probability Induction and Decision Theory. There are over a dozen books in the series, and Bill's was the best, has been the bestseller. Did very well for Cambridge, actually. Let's look at his model and its main features. Now, you can think of this in terms of a real filter with multiple layers. So we have some event or pattern that we wish to explain, and it's going to pass through analytically several layers or decision nodes where we'll be looking at that pattern and asking what explains it. So we start at the top, and our first analytical node is contingency. Did the event have to happen? Or, put another way, was there a range of possible outcomes for the event? Quick example. I actually destroyed a laser pointer doing this once, so I'm not going to let this go. But all of us know what will happen to this laser pointer if I let it go. An object with mass in a gravitational field, if it's free to move, will move towards the center of that field with a probability approaching 1. If I let it go, it's going to go down towards my hand and down towards the floor. There is not a range of possible outcomes for that. So if at our first node, there's only one or a very limited set of possibilities, in other words, the event is not contingent, it had to happen, we refer that event to necessity, to a natural law or regularity. But let's suppose that there are a range of possible outcomes. We'd move to the second node of the filter, and we ask, is the pattern complex? Now, this is something that has this next node of the filter, this node of complexity, has many subtleties that we don't have time to go into. So I just want to tweak your intuitions a bit about how you, in fact, now detect complex patterns, or to put it another way, how complexity of increasing levels leads you possibly to infer design. Anybody? Anything interesting there? To number 3. How about now? How about now? Now. Come on, you guys have all had math. How about now? I see some people nodding. Come on, here. If I do the next one, you're definitely going to get it.
6.
Who said 6? You win. Now there should be no question. 3.141592. Oh, you guys, you're so disappointing. I would have thought that you would have had it somewhere here, and just, 3.3141592. And there's the decimal. Now, most people don't know. In fact, I would guess that if you ask even most mathematicians, they couldn't give you the expansion of pi much beyond about that, because they never use it. Even though this has been calculated out to billions. There are people who do this. I don't know why. Hoping to find, the secret of life or something in there. But as this pattern expands, we get an increasing amount of complexity, and it will become increasingly difficult to explain it by chance. Whereas this just isn't that interesting. There's not enough there for us to say we've achieved any significant complexity. So you can see that there are going to be degrees of complexity, and as the degrees of complexity increase, and we have a match, which is the other feature of Dembski's filter that I'll come to in just a moment, to some interesting pattern, we can only explain it by design. So if the pattern is sufficiently complex where we have to determine what that threshold is, or put it another way, if the pattern is not complex enough, we can explain it by chance. But if it passes that threshold of complexity and also is specified, if there's some independent pattern that complex sequence matches, then we have reason to infer design. Now notice that sheer complexity by itself is not enough to allow us to infer design. If we went outside and walked along the streets of Chopron and came to, let's say, a small park, and there was a pattern of leaves scattered on the ground, or rubble, or a pattern of dust at the side of the road, that particular pattern would be exceedingly unlikely when you consider all the other ways that it could have occurred. In other words, it would be very, very complex. But unless it matched some independently given pattern, we'd have no reason to explain it by design. If that pattern, however, matched, let's say, the constellation Orion, or spelled your name, or gave the decimal expansion of pi, then we would say, no, an intelligence was involved. So this is the only portion of the filter that allows one to detect intelligence. The patterns must be complex, and they must also be specified. If they're not, you explain them here. Now notice that this region, or this boundary, this portion of the filter, makes causal impotence claims. It says that for these patterns that end up here, none of these causes is sufficient. And those kinds of claims are exquisitely vulnerable to refutation. They can be tested. Specified complexity is therefore a reliable empirical marker of intelligent causation. Now, I think that Bill has done quite a bit of good work with this notion of the explanatory filter. He's gone a long way towards capturing in that box all the kinds of design inferences that interest us, plus the other ones that we might want to make. But I don't want to indicate that this conception of design is entirely free of problems. In fact, Ratch, in this book, has a whole section at the end where he critiques Bill's work here, and plenty of other people, Sober, the list is long, of philosophers, mathematicians, and scientists who have looked at this and criticized it in one way or another. But I can tell you that in my lifetime of studying intelligent design and thinking about it, this notion of the explanatory filter has genuinely moved our thinking along. It's a real advance analytically in understanding what it is when we infer design. And I think for most of the things we care about, it works pretty well. But now I want to look at one of the leading criticisms of this idea. I think it's very important that we come to grips with it. What's wrong with these causal impotence claims in science? What kinds of problems arise? I want to look at a mistake, blunder, made by a very good scientist indeed, Johannes Kepler, a hero of mine, a great astronomer of the early scientific revolution, a Christian, discoverer of the laws of planetary motion, and a very insightful thinker, but also someone who was human and fallible and made mistakes. In a posthumously published book called The Somnium on lunar astronomy, Kepler makes the following argument. He says, when things are in order, and that is, when there's some, by that he means some pattern that interests us, if the cause of the orderliness cannot be deduced from the motion of the elements or from the composition of matter, that is, from some natural cause, it is quite probably a cause possessing a mind. Well, you can see that this is kind of a proto-explanatory filter. Here are the natural nodes. These are the natural causes. And this one, of course, complex patterns that aren't specified, can be explained by chance. And what Kepler is saying is, if we can't explain it here, here, or here at these nodes, then it's very probably a cause possessing a mind. So he's developing here a notion of kind of an explanatory filter, namely that. He goes on, if you direct your mind to the towns on the moon, I shall prove to you that I see them. In the spotted parts of the moon, the perfectly round shape of the hollows and their arrangement, or a certain equality of the distances between them, are artificial and produced by some architectural mind. For that scooping out into the form of a circle cannot be accomplished by any motion of the elements. I'm sorry, there's nobody up there. It's actually kind of a boring place to be. There's no one there, no towns. So what went wrong? What went wrong? Kepler was a very smart guy. Where did he make a mistake? Well, I would argue he made a mistake at the first node of the explanatory filter, the first analytical decision point. There are perfectly good and adequate natural causes to produce circular patterns. When my daughters were quite young, they knew that if they threw a stone into soft mud, they'd get a nice circular crater. Or if they threw a rock into a pond, they'd get a nice circular pattern of waves. So contrary to what Kepler asserted, there are natural causes that will explain circular patterns, like the ones produced here by impacts. This, for instance. So he made a mistake here at this node. Now, we might say, well, these are dangerous claims to make then, to say there's no natural cause for some effect, for some phenomenon, and then someone finds it. And you go down in scientific history as being the person who said that we would never fly, or that wireless communication was impossible, and so forth. Namely, you would be known for making a mistake if you made this kind of error and someone found the natural cause. So you want to have a successful career in scientists, avoid making claims like that. This is the problem of induction in science. And Sober, again criticizing design, here now a little over 10 years ago, says, look, the past successes of scientific explanation suggest that what is now inexplicable, now a mystery, may eventually be brought within the scope of scientific understanding. So let's play it safe. Because of the problem of induction, because it's possible for us to err when we use the filter, let's avoid doing it. Let's not allow inferences to non-human intelligence until all natural causes have been tried, until we exhaust every possibility at the first node of the filter. In other words, we'll spend all our time here before we resort to this, because we don't want to make a mistake like Kepler. We've got to exhaust this universe of natural causes first. Spend our time here as scientists. The problem is that's a logical impossibility. It's not just a practical impossibility, it is truly a logical impossibility. Try A and it doesn't work, B, C, D, E, and so forth. There's never any reason to stop. You try n natural causes, n plus 1 remain to be tried. You cannot logically exhaust the universe of natural possibilities for any effect that you wish to explain. It can't be done. This is so important, I'll repeat it. The space of all possible natural causes cannot be searched. That is not how you solve the problem of induction. It's a logical impossibility. Don't try it at home. But you might say to me, but look, Paul, we do infer intelligent causes. There's no natural explanation for that pattern. That guy deserved to be fired by the LA Times. And I agree with you. We do infer intelligent causes, but we don't do it by performing logical impossibilities. So if you think the way to avoid making a mistake in science, to solve the problem of induction, is to logically to exhaustively search the space of natural causes, you're mistaken. We reliably infer intelligent causes without ruling out all possible natural possibilities. We can and do weigh the evidence for and against intelligent causes. So why do most scientists nevertheless hold to naturalism? Well, Thomas Kuhn, a great philosopher of science, died recently, points out that science is a social enterprise governed by shared paradigms. And those paradigms set the problems to be solved in their domain. And they also provide the accepted standards of solution for those problems. And as he points out, to a great extent, these are the only problems the scientific community will accept. So let's go back to Darwin and the Darwinian Revolution. David Hull, professor of science at Northwestern University, points out that the Darwinian Revolution was as much concerned to promote a particular view of science, of the philosophy of science, as it was to introduce a theory about the origin of species. Huxley, I would argue, is the person who more than anyone introduced this view into science and made it dominant. Huxley was Darwin's bulldog. He founded the journal Nature. He coined the term agnostic. And he was instrumental in defining science, namely scientific explanation, as applied naturalism or materialism. I'll skip through this. What Huxley was concerned to advance, and he in fact said this himself, was the fundamental principles of a scientific conception of the universe. Well, what does this mean, a scientific conception of the universe? And is that historically contingent, or do we have to hold that view? Here's a timeline. 2004, National Academy. The statements of science must invoke only natural things and processes. That's our limited toolkit. 1859, Huxley. The fundamental scientific conception of the universe is that it explains things only by natural causes. But let's go back to this guy. Newton said, yes, natural causes are real, but I do not think them sufficient alone for the creation. In other words, there's got to be something more to explain what we observe. So if we go back to our timeline, roughly symmetrical, about 150 years prior to the publication of The Origin of Species, roughly symmetrical with where we are now, Newton argued that natural causes are insufficient to explain all phenomena. Now notice what's happening here. The toolkit of science is not getting bigger. It's getting smaller. What's being ruled out here are intelligent causes that are not human. They're being excluded from science. They were present here in the scientific revolution as causal possibilities. And what happened in the 19th century is the toolkit of science got smaller, so that what we have now, what we can appeal to now to explain things like the origin of life, is a smaller set of causal possibilities than Newton would have recognized. That, I think, is interesting. Here are the phenomena that we wish to explain. Here are the possible causes. And what Newton argues is when natural causes are at hand, God uses them as instruments in his work, but I do not think them sufficient. So we have some effects here that we can explain by reference to natural causes. But there will be others, Newton argues, that are not explained by natural causes, and we need something here to account for them. Well, here's what naturalism, methodological naturalism, does. It eliminates those possibilities so that when we come to explain the phenomena, we have only natural causes in our toolkit, and effects caused by non-human intelligence will not find a corresponding cause because it's been eliminated. It's been taken out of the toolkit of science. As a consequence, there's a fundamental logical asymmetry between intelligent design and naturalism. And it looks like this. Intelligent causes add something to the toolkit of science. They take nothing away. This is bigger than that. And once the scientific community comes to understand that, I think the situation in terms of the debate about intelligent design has got to change. That is a larger toolkit. That's a better toolkit, even if there's nothing here for which we need this. At least we have it available. Now, I've run well past my timeline, so I'm going to skip through this discussion of natural and supernatural, which we can save for later. And I want to get to my last slide. I do want to point out this, however. I think that science would be more free and more honest without a rule it doesn't need, namely methodological naturalism. I think the great promise of intelligent design for science is that it gives us a richer field of possibilities than that provided by naturalism. Edwards is a mathematician in the United Kingdom, a very insightful probability theorist, and he points out in this book, Likelihood, dealing with scientific explanation, that the essence of scientific investigation is first an acute sense of curiosity, and secondly, great power of imagination. For the richer the field of imagined possible explanations, that is, causes, the greater the chance of a satisfying one that comes to the truth. Here's Drosophila, a little arthropod about whose genetics and development we now know a great deal. And here is a diagram from Science recently showing the network of interaction of proteins for part of Drosophila. And this kind of complexity, this kind of systems complexity, is increasingly the bailiwick of biology, that to understand a creature like this, it's not sufficient to reduce it to its molecules, but rather one needs to understand the complete range of interactions of proteins. Proteins like this that I showed you previously. Every cell in your body that produces proteins has this chaperone. It's a nursery for baby proteins, which fold here, isolated from the rest of the cytoplasm. What accounts for the origin of a structure like that, a multi-protein complex? Are natural causes sufficient, or do we need something more? Or are we going to say we don't know? I'm done. That's what we need. Think about it this way. Let's go back to our island. Taking this off does not mean we're going to do that. What it means is the whole island will be open for exploring. Sorry, I ran a bit over, but I have a signal from the back that I need to stop, so I'll stop now and maybe take questions for a few minutes before Fred begins. Thank you very much. You've been very attentive.
We're going to have coffee now in the hall outside.
Yeah, maybe I could even. I was actually not raised in a Christian family, and I some ways fit the American imagery or something. But I was raised actually in a log cabin my father built, and that's not very common anymore. My parents are rather eccentric, but they had not. Of course, they were not believers, and but my father was very strict. But one thing I remember as even a very small child, having being out and living in the woods, and just seeing all the wildlife around me, and I was convinced of intelligent design. And even though my father didn't believe it, that was the one thing I didn't have the courage to talk to him about it at that age. But I disagreed with him on his claim that there was no God behind it all. And I remember seeing an apple tree that was growing there and saying, "We didn't invent this, and it's right there for me to take one and eat one." And I said, something's going on here. All right, so what I'd like to do, and this is really, I have my own sort of unconventional take on intelligent design in a way, because it's been something I've been thinking about since before there was sort of intelligent design movement or anything like this. But as soon as I saw Bill Dembski's book and read it a number of years ago, I recognized immediately its significance and as an important step. And I think that there are still a number of things that need to be thought through and worked out. But that I think it's something of interest apologetically and also of interest scientifically and philosophically. And so I think it's an interesting thing that we should, and something well worth giving some thought to. So there's so much I could talk about, and I'll just really only have time to briefly discuss a few things, but I'll give a kind of an overview of just how I see this whole question of intelligent design, which was defined somewhat for you in the last talk, some of the definitions, and I'm going to rely on that as a kind of foundation for some of what I have to say. And I think one of the important things scientifically, and one of the things that has greatly, on the other hand, greatly clouded this whole issue is the confusion over terminology. People use the word order, disorder, complexity. Complexity in particular is the most abused word, I think, scientifically, in this whole discussion. And so I'm going to try to at least introduce some more distinctions, which I think are helpful. And I'm not sure we're done making the distinctions, but part of, as understanding develops, we have to sort of sort out the categories that we can use, and that helps. And in particular, I think that one of the big interfaces in physics now is the interface with biology, all right? Because there's a tremendous forefront, and some of you in the audience I know are actually involved in this, because now nanotechnology and microphysics, solid-state physics is now sort of connected with biology. And so as a forefront of research, these two are coming together. And the one question is, well, how do you apply physics to biology? And I'll make a few comments about nonlinear dynamics, because this is an area that I have had some professional work in, and that it's also brought into this discussion in often very confusing ways. Thank you. And so then I'll talk about the place of the design inference really in physics, and I'll give a little brief sketch, and I won't have time to go into great detail of really operationally as an experimental scientist, sort of how science works in a general sense, and show its openness, that it's not this hermetically closed system of just reason and observation that the materialists and the rationalists assume. And so, and address a number of questions relative to, the apologetics. But I'm happy to be interrupted at any time with a question, and I hope to, and anyway, will be instructed to stop at some point, so we'll have time to talk at the end. So I mean, the first thing is that from often in these arguments, there are statistical arguments, and statistical physics is invoked. And even though Darwinism is a theory of biology, it somewhat pretends to be a statistical theory in the sense that there's a claim that things tend to evolve according to a certain way, and the idea, it's following a kind of paradigm of statistical physics. But there are categories which I think are very important to make distinctions, and when you enter these other categories, you have to realize that your theoretical apparatus needs to be adapted to deal with what you're looking at. Otherwise, you'll do great violence to the subject. For example, order and disorder, we have the traditional fields of thermodynamics and statistical dynamics have to do with dealing with order and disorder. The difference between things all being the atoms in a solid crystal where they're all nicely ordered and arranged, so that you can actually, just with a small specification called a unit cell, say, okay, the atoms occur in a certain pattern, and this pattern simply repeats itself. This is order. Disorder then happens when you can have a transition to disorder. You heat up this crystal and it may melt. Now the atoms are all sort of bouncing around. And so these transitions between order and disorder are the proper subject of statistical mechanics and thermodynamics. And you have, the operations of law. And in understanding disorder, we make use of ergodicity. Just means there's a space of possibilities. For example, you have these atoms, and at one point they were all, when it was a crystal, they were all nicely lined in rows. Then when you melt it, they're all over the place. And the ergodic hypothesis says, well, at any one time, of course, you'll have a very particular arrangement of them. But if you wait over time, they'll just take on every possible orientation that's consistent with the amount of energy that they have. And so one thing that's very important to recognize is that energy. These things are all somewhat coordinated by energy considerations. Energy is playing this sort of defining principle. So in other words, for example, in disordered systems, it's not just anything's possible. We consider all the possibilities consistent with a certain amount of energy available. And energy is, in fact, what's involved in the decisions, if you will, of when the thing will become ordered or disordered. All right? So, for example, people say, look, no problem creating ordered things. And it used to be thought that life used to be classified as ordered, because they said, well, things are all... so then they said, well, no problem explaining for that, using thermodynamics. We know that we can freeze things, and so therefore you can create order very simply, and therefore life is just like freezing water. And, but that's, well, we laugh now, but actually many people were saying that because they hadn't really thought it through a little bit deeper. Now, in relatively recent times, although I would say for over 100 years, there's been a recognition that actually dynamics isn't always so simple. And if you go back, in fact, in the 19th century, they recognized that mechanical systems are often unstable, and then they produce very complicated situations, even things that are nominally simple. And I'll give an example later. And so complexity is still a very broad category of disciplines, including, for example, chaos, which is just a sort of a fancy or a buzzword almost for what really is nonlinear dynamics. All right, so that's the science of nonlinear dynamics. And self-organization is also kind of nonlinear dynamics, but tends to include systems like fluids. All right, so for example, clouds under the right circumstances will line up in rows. You can look out in the sky and the clouds look organized. And they seem to do this without somebody going up there and shoving the clouds around to organize them. And so that's called self-organization, right? But of course, these things are also governed by energy considerations. In other words, the clouds just don't do that because they feel like it, and they say, well, I'm going to self-organize myself today. They do it because, of course, energetically it's favorable. In other words, so in other words, it can be subsumed often into these kinds of considerations of order and disorder and these principles, but you have to be careful how the energy is getting sorted. And so the complexity actually contains elements of what we would call law. In other words, these very simple principles which you can articulate with, say, equations of various kinds, differential equations. And also contains elements of the statistical physics. In other words, there are a certain amount of things which you then treat according to statistical techniques. Now, but there's another kind of level of complexity, and beyond those represented by chaos and self-organization, and this is specified complexity. Okay, and this is a kind of complexity which was outlined to you in the previous talk as well. But I think there are different kinds of order. One, of course, is now imagine you have the atoms instead of in a lattice or instead of in a liquid, you set them out in a way so as to spell a sentence. All right? And this, on the one hand, obviously involves the infrastructure of the matter, but it also transcends it in that without, in fact, the detached pattern, which is in this case the understanding of the language, which you would use then to decode this message, it becomes somewhat indistinguishable. But what's interesting is that in biology, these kind of arrangements actually have teleological consequences. In other words, they actually have function. And so the borderline, I mean, people would like to have this borderline, which Paul described last time, of just saying, well, we don't consider anything teleological, in which case you can't study biology, I think. And I'll give some... So this information and complexity, these terms, and I'll indicate briefly how information theory came out of studies of statistical mechanics. There often these terms get confused, and they are so abused in this whole discussion of intelligent design in the popular discussions because, complexity, well, lots of things are complicated. From a mathematical point of view, if you take your garbage can and dump it on the ground, that's a complex situation. It's a really, and it would take many, bits of information to describe it. But it's a dysfunctional bit of complexity, and so it's not the same thing as a text which is organized and which actually, in a way that's intelligible, or a cell which is actually functional and does things. Okay, so this question of order and disorder is not the same thing as complexity, right, which contains both, nor is complexity the same thing as function and non-function. And often when people talk about intelligent design, they say, well, those intelligent design people, they just think everything's too complicated to explain by natural law. And that's not the question, because the word complexity there is being used in a very vague and sense, which is not very helpful. So physical law discriminates on energy and geometry. Okay, if you look at all statistical theories, they are either using topology or some sort of geometrical arguments or energy arguments, and these are what structure what they're observing. But in biology, you have teleology. It's displayed in function and mechanism, and they're not determined by the geometry or the energy. In fact, they're obviously geometry is involved in describing them and energy, but those are not fundamentally the. So, for example, people will invoke natural selection. Now, as someone doing statistical mechanics, I can tell you that natural selection, it's a word which gives you sort of an idea of, it's a loaded word because it has teleological overtones. When you hear the word selection, you hear teleological things. You think like, oh, someone's choosing something, right? But that's, of course, not how it's meant. What it's meant is natural selection is simply an interaction. It's an interaction with the organism and its environment. And I can tell you from every statistical point of view, energy and geometry point of view, the environment selects for dead things. All right? That's what it selects for. And so you should expect the natural result of natural selection to be everything dies. And that's what's missing, of course, in the Darwinian evolution. There's no mechanism, there's no energy function which says it ought to happen. In fact, all the energy functions say it ought to die eventually. And of course, things do eventually, but what's remarkable is that they persist. All right, so the information theory, and I'll talk a little bit more about that later, but information theory is just trying to was actually a science invented to deal with the transmission of messages, okay? Claude Shannon worked at the Bell Telephone Laboratories, was interested in communicating telephone communications through channels and how to make that successful despite the environment of noise which can accompany any kind of transmission system. But it's very important when people talk about information theory, they also equivocate on the word information. The word information, when you hear information theory, does not mean the daily news. It does not. Claude Shannon, and I'll give another quotation, says, look, frequently, of course, messages have meaning. Okay, and we'd say, yeah, of course. Now he's saying that's actually irrelevant to my engineering. In fact, his engineering problem, and we should say the engineering problem actually, in context, what he means the engineering problem is his problem as a telephone engineer of transmitting information across a transmission line. For that problem, it's irrelevant. In biology, by the way, it's not irrelevant. Okay? But for telephone engineering, it is irrelevant. In other words, whether or not the messages have meaning is completely irrelevant. So when people use the measures of information and talk about information, you have to realize that there's a very important distinction, which the thoughtful people like Claude Shannon, and another example would be Leon Brillouin, who is one of the founders of information theory, a famous physicist, was very aware of this, and he said, look, the present theory of information completely ignores the value of the information handled, transmitted, or processed. This point has been carefully emphasized throughout this book. Many other writers seem not to have realized the importance of this restriction, and many misunderstandings about the possibilities of the present theory resulted from this situation. For example, people can say, look, here's a dynamical equation which generates complexity and information, and therefore people say, see, no problem creating cells out of nothingness. Well, what is being created is, sure enough, can be described by information theory, but it's not meaningful. It may be completely just like your pile of garbage on the floor. All right? And so this equivocation, Brillouin was already very familiar with this problem, and this is actually decades ago. And so he said, look, it's only by ignoring this human value that he's constructed his statistical theory. Okay? However, there are many problems that cannot be discussed along these lines. In other words, he's recognizing that there are important scientific questions, namely biology, which you can't address without generalizing somehow. And that is exactly what intelligent design is trying to do. It's trying to generalize as much as possible our understanding of order, of certain kinds of order, to be able to deal with for example, biology, and understand it in statistical terms. So again, he says whether or not the message made sense either to the sender or receiver was regarded as completely irrelevant. All right? And so that's very, very significant because in biology, there's not just complexity. It's not less like a pile of sticks or something. It's actually things where they're coordinated and they actually achieve functions, which are teleological. Now, one of the most famous people for promoting the Darwinian idea and developing it in the modern times was Jacques Monod, who wrote a famous book called Chance and Necessity. And it's interesting to read chapter 1 of his book, because even though he says, look, we have to, he comes down on the side of materialism, it's very important to realize that he realized that this was ridiculous. He did. And if you look at chapter 1 of Monod's book, he develops his whole side, and he emphasizes over and over and over again, he says, oh, we can't consider intelligent causes. We have to, in order to be scientists, we have to have this objectivity, what he calls the objectivity of nature. That is, you have to refuse that any explanation in terms of final causes, in other words, in terms of teleology or purpose, that can't be true knowledge. Now, this is this arbitrary rule that the materialists are adding, which Paul talked about, which I think actually there's no warrant for this kind of rule that he's saying here at all. And in fact, most scientists haven't operated under they've rebelled against this rule because it otherwise totally stultifies. It's a science stopper, okay? That's what this is. So, now, because then Monod, actually, here he is, here's a champion of materialism, okay? Other people say that life just arose from natural processes. He says, nevertheless, objectivity requires us to recognize the teleological character of living things, to admit that in their structure and function, they perform a project. That's teleology. He's just saying, as a scientist, just looking at these things, you can't escape the fact they're teleological, all right? This is not a paradox or miracle, it's a flagrant contradiction. In other words, he's saying, what I'm trying to do as an atheist and explaining things just in terms of materialism is, in fact, a contradiction. It does not respect the very nature of biology. Interesting statement. Now, he's an existentialist, and for an existentialist, life doesn't have to make sense anyway. And so, no, seriously, I mean, life is fundamental. No, if you understand existentialism, life is fundamentally absurd, all right? And so, it didn't bother him, but he has the honesty to say, at least up front, you know what, doing this really contradicts the very nature of what you're looking at. And he won a Nobel Prize for his work on the transcription process of information being transcribed out of DNA and into the construction of parts of living organisms. All right, so this generalization process of taking the ideas of order and disorder and thermodynamics and generalizing them to try to deal with biology has a long history. It starts, I think, with James Clerk Maxwell, who is actually an interesting Christian physicist who is one of my heroes. And he, in fact, was one of the founders of statistical physics in the 19th century. And so here's a little device, in fact, which Maxwell was involved in trying to understand, a thing called a Crookes radiometer. It has little vanes. Maybe you've seen them. He's in little curiosity shops at science museums and things like this. And when Crookes originally submitted his paper and Maxwell reviewed it, Crookes said, look, well, light strikes it, and that pushes the vanes around. Well, the problem with that explanation is it turns the way these arrows are right, and people who understand physics say, wait a minute, the black side absorbs light, the shiny side reflects it. Well, actually, the reflecting side gets more momentum because the thing comes in and ricochets off, and you get twice as much momentum, so it ought to be spinning the other way, right? So they knew something was wrong. Well, then the next thing was maybe it's pressure, right? And Maxwell realized, no, it can't be pressure because pressure equalizes so fast inside there that it's not a pressure difference. And so it turns out that the explanation has to do with the microscopic picture of the molecules, that even though the pressure is the same everywhere, the temperature and density are not the same everywhere in there. And so the sides here, these dark sides actually do get hotter, all right? So the temperature is higher, but the density is lower, all right? And the pressure is the same, so the pressure in the center of the plate on each side is the same, so it wouldn't push that way. But right on the edges of the plates, the distribution, in other words, the velocities of the atoms are not the same, all right? And the hot side tends to get kicked more this way. So it's an edge effect. It's very subtle. It takes some time. I wrote this out for myself and realized I don't have time to explain this. So if you want to talk about it later, we can talk about it. But it's a very interesting problem which kept a number of these people very entertained back in the 19th century. Another modern-day example of this, well, Maxwell introduced, he understood that there were limits to the second law. It was basically a statistical theory. The statistical theory of the second law says that entropy, in other words, that the amount of disorder, in a vague way of saying it, will tend to increase with time. In other words, things will tend to distribute themselves so that they will take on all possibilities consistent with the energy available. And so, but Maxwell said, you know, this is really a kind of a statistical idea, and all the laws of physics are reversible. So you could imagine a little, you know, someone that could open and close doors at the microscopic level, allowing molecules to go through, and opening the door every time a hot molecule comes from one side this way, and closing it otherwise, and opening it so that you could actually, with just opening and closing a door, supposedly, make heat flow from cold to hot, all right, which violates normal thermodynamics. Normal thermodynamics, heat flows from hot things to cold things. If you have your coffee, if you have your coffee cup there and it's hot, it will cold. It'll become cooler. Now, it would not violate the laws of mechanics for your coffee to get hotter and hotter and hotter and finally blow through the roof, all right? But no one worries about this because they believe in the statistical theory that the molecules will tend to distribute themselves in such a way as to maximize the entropy, in which case the heat will flow from hot to cold, your coffee will cool off. And so many people were inspired by Maxwell's sort of reflection to think, well, could you build a device then that would be a perpetual motion device? And this is a little gadget that was sort of conceived by Richard Feynman, another famous scientist. And what he said is, look, you could imagine having molecules inside this little container that bang into these vanes, and then on the other side, what you do is you have a little ratchet and pawl. The pawl is this little latch that pops in there and stops the ratchet from rotating this way. Just lets it go the other way. And you would think, well, the molecules will bang into here randomly, but they can, because of this ratchet, they'll only be able to turn this way, and this way I can make heat do work just like that. And this violates, actually, the laws of thermodynamics. And so what Feynman noticed is that, look, when this thing gets banged and that little ratchet goes ka-thump, well, if energy were conserved, it would just go bump, 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 bump. It would just keep rattling away there forever. And he said, well, okay, so if it doesn't do that, energy is dissipated over here, and so everything in this box is going to get hotter and hotter and hotter. All right? Now, eventually, it will reach a certain temperature where something very non-intuitive will happen. Now look at this ratchet. You know, if it's rattling like this, banging, 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 if you were to rotate the ratchet now in the opposite direction and it comes slamming down, it'll actually rotate, spin the thing in the opposite direction to what you'd think. In other words, it'll start rotating the other way. And if you go through the argument carefully, which I don't have time to, but I'd be happy to show you, that actually, when these two are the same temperature, this thing doesn't go any more to the left than it does go to the right. And this little pawl thing is banging away because it has energy consistent with the temperature over here. All right? And so this thing doesn't actually end up doing anything, and it doesn't violate the second law. Interestingly enough, though, this little gadget is a very good model of how molecular motors actually work thermodynamically. All right? And they exploit, in fact, the fact that inside these cells you don't have the same temperature, so you can make little molecules inch their way, and they're actually, in some sense, exploiting what's called Brownian motion of the molecules, and they are able to perform a directed motion. All right? So inside cells, you don't have this, you know, thermal equilibrium, and so therefore you can make little molecular motors literally take the garbage out. They take some garbage molecule, come to the up, another molecule opens the door, throws it out, close the door, go back, get some more garbage. So, but nevertheless, so the reflection on this led to some very interesting advances in understanding of how heat moves through machines effectively. Now, but it wasn't actually a full resolution of Maxwell's paradox. Because Maxwell said, no, you would have an intelligent, you know, he proposed a little intelligent being which became known as Maxwell's demon, although I think that that terminology didn't come from Maxwell himself. Laplace, a number of years earlier, had used this concept with respect to mechanics. But, and so if you know, the idea that if you just open the door at different times, you could make all the hot molecules be on one side and all the cold molecules be on the other side. And so on reflection, what people realize is that, well, if you have any material machine that you want to make do this, it has to know about the molecule coming. It has to have that knowledge, right? To know that it's time to open the door because a fast molecule is coming. Well, how are you going to measure that? Well, you could shine a flashlight, right? Now, you shine flashlight, you're injecting, actually, entropy into the system, right? And so it turns out that acquiring the knowledge that you're supposed to open the door requires you to expend some energy or increase entropy in some way. And so that actually even any device which depends on its purely material will always have to invest energy to get knowledge and information. In other words, and so when they quantified this, they found that actually information itself can be thought of as the antithesis of entropy. Because think about it, if you have molecules banging around in a box, you have a certain amount of entropy. The entropy increases actually if you give it a bigger volume to bang around in because there are more possibilities. Entropy is simply a measurement of the number of possibilities available to you with a certain amount of energy and a certain amount of material. Now, if I slice that box in half, just slice it in half, what's changed? Have I reduced entropy? Only if I know where the molecules are. Like say there was only one molecule and it's moving around in a big box, it has a certain amount of entropy. I slice the box in half, it's only reduced, the entropy is only reduced if I know where the molecule is, all right? And so then, but now slice it in half, I've done a binary operation, all right? It used to be a full thing, now it's in some one half or the other. Now the reduction in entropy could only be achieved if I were to obtain one bit of information. Namely, the bit is it in the top part or in the bottom part? A bit of information is just simply a 1 or a 0. Saying 1 means it's in the top, 0 means it's in the bottom. And so by equating the changes in entropy with the necessary information you'd need to specify, all in this case information just saying, how would I specify the configuration of this thing, right? Then there came to be an understanding that information and entropy are somewhat opposites of each other. All right? And in fact, Brillouin introduced the term of what's called neg-entropy, or negative entropy. But again, you have to recognize that this does not have to do with information in terms of meaning or purpose or function. It's information just simply in terms of how do I specify where everything is. I have atoms. How do I specify where they are? If you know where they all are, suddenly entropy is much less because you know exactly where everything is and you've ruled out all the possibilities. So the more information you have, the lower the entropy. Same way in terms of specifying the configuration of physical things. So it's in this kind of way that the ideas that applied in the old days just simply to order and disorder are now becoming applied to complexity because you can just use information as a way of specifying whatever it is, the configuration of things. All right? But there's another level, of course, beyond that, and that is So this led to, and Szilard and Brillouin are two physicists who were involved in this, and who basically said, look, we have to generalize the concept of entropy to include the idea of information, because it will, in any given situation, determine really what the possibilities are. And so this is just simply written out here what I just said, that there's complete with a little formula. And so they said, now when you take this all into consideration, there's no way to violate the second law of thermodynamics, even with respect to information. And so, but there's a very interesting thing here. All of these arguments really apply to something which you could build. All right? You could actually, these things, even though Maxwell's original thing was a little being, that intelligent being that opened and closed the door, all the theories of Szilard and Brillouin all saying, no, let's just get the living thing out of there and just imagine a machine doing this, and the machine is fully realized you can't violate this generalized second law. All right, and it helps you understand. This generalization has been very helpful in information theory, and so in understanding how to send messages, how computers function, and it's extending physics to deal with information-bearing systems. But nevertheless, of course, it does not deal with this next level of distinction, namely, what does this information mean anything, and is there any purpose or function to any of the information? So now, what Bill Dembski has tried to do, and this is in his book called No Free Lunch, is to generalize the second law of thermodynamics, not only as in information theory, but then to go to another level to try to deal with the idea of design inferences, all right, which has to do with how you can recognize the fact that an intelligent agency has been at work, okay? And so his generalization is that, look, the way you recognize intelligent design is by what's called a detachable pattern. That's in his outworking of the design inference. And so his claim is that, and which I think is true, although it still needs to be, I think, worked out in all its details, is that there may be some way to objectively identify the fact that intelligence has been at work, and that natural forces can only destroy that impression of intelligence and not create it. Okay? And now there are other ideas, and Roger Penrose is another physicist who's not a Christian, but who has recognized that and he's developed this in some of his writings on the mind, that human beings do things that machines can't. All computers operate algorithmically. They have instructions, or either they're random or they have instructions. And that space of possibilities is less, and that Gödel's theorem has to do with the incompleteness of mathematical constructions like operating systems for computers, and that people do things routinely, like prove theorems, which computers can't do. That's Penrose's theorem. So, which is a corollary, really, to Gödel's proof. Anyway, it goes along with Dembski in saying that, look, there are things that intelligent agents do that other things can't, all right, that nothing else can. And this idea that law and chance, in the words of Monod, completely can explain everything, right, is actually an unreasonable, in fact, it's self-contradicting, all right? And why is it self-contradicting? In line with Gödel's theorem, if you commit yourself to a mathematical theory and say everything fits in this mathematical theory and nothing is outside it, you've just contradicted yourself. That's Gödel's theorem, is that if your system is closed and hermetic like that, then it's also false. And so there's always going to be open-endedness. And so that's what we're trying to get at here, is the limits of what you can explain by means of principles. So I'm trying to explain what Dembski's extension of the second law. You have this system carrying information that performs a function, say a living cell. All right? It has lots of information in it, information in every sense of the word. It has very detailed configuration. If you were to try to say all the molecules are, it's going to take a lot of ones and zeros to specify it. Now, but not only that, it performs functions. Now, take this thing and subject it to noise. In other words, selection, just an interaction with the environment, right? That is going to tend to destroy the content of that. Because, why? Because this thing has a relationship to a detached conceptual pattern, namely function. For example, cells move. That's a function. They just move from A to B. You have to work out a whole number of engineering problems. The more you know about engineering, and my undergraduate degree was in engineering physics, and I took lots of engineering courses, you realize that the operations of a cell, from an engineering point of view, are remarkable. And especially to get a machine that constructs itself and repairs itself and then does the function. You're talking about engineering on a level. And this is why people are so interested, by the way, in biotechnology, because it's superior engineering. It's engineering on a level beyond what we know how to do. And so everybody wants to copy it and exploit it, which I think involves some dangers. But nevertheless, it's a engineering on a very sophisticated and high level, which has a correspondence to a detached conceptual pattern. That, in this sense, with function, it can become very explicit, very tangible. All right? That's why to deal with biology, we're forced with dealing with intelligent design. You know, something like mobility is something that we can specify. We can say it has to have the wherewithal, using thermodynamic cycles and things inside it to move itself from here to there and to do what it needs to do. It produces toxic waste inside itself. It has to come up with a way of opening the door and throwing the garbage out, or it will die, right? And so you have a number of functions. These functions are teleological. That's what Monod, even in his existentialism, was recognizing. He said, you can't deal with biology at all unless you recognize there are functions going on here. And so that's a detachable conceptual pattern, which is what Dembski calls it. And that means they've satisfied this. Now, you subject them to an environment which basically is disorganized and tends to just kill them, right? Now, you could say fitness means that some things are easier to kill than others, but the fact is that the environment's not telling you how to survive. It's just trying to kill you. If you manage to avoid being killed, fine, you're more fit, but it's not telling you how to survive. Right? It's not informing you. It's not instructing you. Well, listen, if you built this little molecular machine, you'd be able to move that better. You know, it's not going to tell you that. It's just going to try to kill you. And that's, you know, what the environment is doing to these little cells. So his theory, or the generalization of the second law is saying, look, this is not going to tell you, it's not going to accomplish this for you. This is something else. And it interacts with the random, disorienting kind of environment and isn't going to increase the specified complexity. All right? So it's not going to strengthen this connection by making this connection. All right? That is the essence of Dembski's, what he calls his no free lunch theorem. And I think it's true. So if you take a book, it has a certain correspondence to the author intention. You take that book and you leave it out in the rain and, you know, and wash it down. And some books will survive better than others. There'll be a natural selection there. But in the end, the correspondence with what the author wrote will not be improved or repaired. It'll just be lost with varying degrees. And that's essentially what's being stated. Okay, so I don't have time to talk about this. My own thinking on this is in slightly different sense from what Bill Dembski has done, but it's I don't have time to explain my own ideas on this, but because I know I'm going to run out of time. But anyway, it's not too. The fact is that this opens up a whole range of very interesting questions, you know, and they have to do with the interaction of physics and biology. And I think that this slamming the door on intelligent design, saying, "Well, it's just a bunch of lunatics who, you know," is ridiculous. These are questions which are actually prompted by the study of biology. And okay, I don't have time to, you know, in mechanics we deal with phase space. That has to do with these denumerating the space of possibilities. But one thing I will just say about this picture is, one of the things that's made this whole area so difficult to penetrate is that counting is a very difficult thing. You might think counting is easy, but counting is very, very difficult. It's the heart of statistical mechanics. People say, well, how likely it is that life just arises from non-life? Well, in order to formulate a statistical theory, you have to be able to count the ways that it could happen and the ways that it can't happen. And then you have to make some sort of assessment. And this counting is extremely difficult. But I think it's an extremely important question, and that I don't think you can say that there's no way to make progress on this. I think that actually, for example, one of the things that people are going to do with biotechnology, which could be very harmful, they're going to build little machines that they're going to sort of send out and try to collect information on you from. You know, so there'll be little designer, you know, organisms which may perform harmful things. But and you might want to be able to detect them. And so you're left with the question: how could you tell if this little molecule that's banging around is actually a designed thing with some teleological function, or just some sort of environmental factor? And so these questions of being able to perform intelligent design, I think, are going to become very important for good or for ill. So now okay, so this is part of my own explanation. I don't have time to go through, but all right. Basically, the heart of what I'm saying here is it's whether or not a configuration of things is improbable. That's one question. Then the question is the state, the sequence of events that happen. When you watch something and it does some behavior, some function, that's another piece of information that's beyond just looking at how improbable a given configuration is. So that's how I'm going a little bit beyond what Dembski's talking about. So one of the things I wanted to talk about, and I don't have time to talk about too much, but is nonlinear dynamics, because people often say, complexity. Nonlinear dynamics produces complexity for free. And it's true. It does produce complexity, but of the sort, and it's a little bit like the complexity of the pile of garbage on the floor, only it's prettier, okay? And so here's an example which is analogous to a problem I've done in my own research. And this is a compass, which, for example, you would use to tell the direction north. But now you do something rather unpleasant to this poor little compass. You put it in a magnetic field which is oscillating back and forth. All right? But periodically, perfectly deterministically. Well, it turns out that this thing will actually start wandering, not in any ordered kind of way. It'll look very disordered, and it'll look, in fact, random. It'll even satisfy this ergodic hypothesis, which I talked about before, which people said, oh, that's a test of randomness. But it isn't random. You can actually compute what it's doing using Newton's laws of mechanics. And so this is a simple example, and I'm going to show you some of the pretty pictures here. I just made a little program on my laptop to describe this little compass, just to give you an idea. And these pretty pictures here, you can see ordered. This is this orbit here, this purple circle, corresponds to, in fact, the compass. As the field oscillates back and forth, it's rotating nearly synchronously. It's actually wobbling a little bit. That's why it's going around like this. And so it's running almost like an electric motor. But you find here, in fact, near this point here, there's always a little bit of fuzziness. And as people began to study this, by the way, was recognized by a fellow by the name of Poincaré in the end of the 19th century, but nobody understood what he was talking about. So, and then if you change some of the parameters of that little motor, it starts becoming more, so it can operate, depending on how you start it. Sometimes it can operate in a very ordered way. Sometimes it'll wander randomly. And I have actually, I couldn't bring it with me, but I have one of these that I built that is very dramatic demonstration of chaos. And so what you see here is something that looks like randomness, but embedded in it you have still ordered patterns. And people said, here is a very simple device producing a very complicated picture. And as you change the parameters just slightly, you get different pictures with all kinds of interesting, complex patterns. And nested in here, in fact, you have infinite complexity. In other words, you have pictures with this kind of, that if I were to then numerically, with my computer, zoom in and say, what does it look like in a small? You'd see the same picture. What does it look like in small? Infinite and forever, right? So it's something which is infinitely articulated and complex. And yet, it's not functional. It's just a very pretty picture. It does describe the mechanics. But this should not be confused with the cell, right? This is not a living thing. This is just an interesting, pretty picture, which has structure in it of a certain kind. And so to say that complexity theory or that chaotic dynamics explains living things is just simply erroneous. Okay? It's a category error. It can produce complexity, and I would even say that we should expect to see nonlinear dynamics in cells and in biological things. So this kind of mechanics is part of biology, but it's not going to explain biology, not the part which makes the cell do functions. All right, so I'm probably already out of time, but anyway. So
well, you've got another 20 minutes.
Oh, great. All right, so I want to... Often people will say, well, you know, and even I'm not contesting the explanatory filter which was presented to us, but I think that's interesting. We have to remember what constitutes an explanation. And in science, I think that science itself, the whole operation of physics, is in fact a design inference and was seen as such by those who founded modern science. And again, one of my favorite examples, although Newton would be another example, because if you remember in the quotation of Newton that was given to us, Newton didn't say, well, sometimes there are natural laws and other times God's there. He said, sometimes there are natural laws and God uses them, but they don't explain creation, which is different. He's saying that even when you have natural laws, they didn't just come out of nowhere. They do not in themselves constitute an explanation. They are in themselves in need of explanation. Right? When I observe gravity and I say, okay, it's gravity, I haven't really explained it. I've given it a name. I can describe it mathematically, but it's not an explanation. And so we should not pretend that, okay, you know, eventually we'll explain everything. Science never will explain anything on a deeper level than I can describe it mathematically. And an even stronger statement comes from James Clerk Maxwell, who said, look, belief in design it's a necessary consequence of the laws of thought acting on phenomena of perception. This is a way of summarizing, in fact, what the whole thing you do in science. You're looking at phenomena, and you're trying to understand it, and you're saying, I believe there's some design here. There's something here, and that design I will try to capture in my theory. So the whole scientific process is, in fact, a design inference. And so, I mean, you know, thinking God's thoughts after him, Bacon, right? He was tremendously important in the minds of early scientists. Well, what is that? That's a design inference, right? It's saying there's a detachable pattern which I can represent in terms of a theory, and that will be not just a, the fact of gravitation is not just the happenstance of this. There's something deeper. There's something detachable, a theory which I can then extract from this, which helps me to understand the purpose of the whole thing. And so, of course, this brings us to my simple description of how science operates, and there won't be time for me to explain all of this, but again, there are a lot of assumptions in the operation of science. As a scientist, and you go into the laboratory and you work, it's a very open-ended process. It's not this hermetically system where you could just turn the crank and knowledge comes out, or you just use logic and look and make observations, and then science happens. It's not true at all. There are a tremendous number of value judgments, open-ended things, intuition, all kinds of things which are coming into play. And people who do science recognize this. But often except for the materialists present it to the public as if, no, there's nothing involved except for just reason, which is, I think, just simply dishonest. It's not how science operates. First of all, science operates on faith, right? There's no contrast between science and faith. Science operates on faith. Without faith, science comes to a screeching halt, all right? So absence of faith, atheism is a science stopper, all right? Why? Because unless you have this faith that there's an objective reality there that you can somehow, despite all the limitations, all the epistemological limitations of the human being, all the problems, the variables that you maybe can't control, somehow it's not futile to do this experiment. And only people who have struggled in a laboratory for many months trying to make something work realize how much faith it takes to keep going when it looks like it's just hopeless. And really, it is the foundation of scientific operation. And you make some sort of observation, yes, but by faith you believe that somehow it's intelligible, somehow it's separable, somehow it's going to be within some sphere that you can grasp as a finite human being. And you do some analysis, and you don't pretend to explain everything, right? You explain only what you can control. And I think it's reasonable to assume that human beings don't control everything. And so you can only analyze some things. But nevertheless, what we find is that analysis is hopeful and produces the possibility of a generalization. This is this detachable pattern. This is the design inference. It's saying, I think there's something going on here that isn't explained just by random banging around. There's a principle at work here somehow. And so that principle leads to, once you find the correct representation, it leads to the construction of a theory. All right? And then once you have a theory, you say, well, if this is true, what are the consequences? Right? And you must look at that. And then, of course, application, open questions. Now, where did this come from? This is, and if you look at, I would say, Michael Faraday, the paradigm of experimental scientist. And he, of course, was a preacher also, right? And this is a picture of the Reformation theological method, right? Only it's an image of it. Theology being the queen of the sciences, all right? And nowadays people find that statement unintelligible. But actually, I think it's actually very intelligible in this context. You have God revealing himself in his word, and you read it and you say, despite all my epistemological limitations as a human being, God has somehow made it possible for me to understand. And so by faith, you actually do the experiment, okay? And so it's based on faith as well, right? But so science was too. And it's a faith in the goodness of God, right? Now you do analysis, generalization, you construct theology. Now you realize your theology, it has to be tested. And you look at, well, if that's true, what are the consequences? We always have to, and this also, applications has to do with life. You have to, biblically, you can't say you understand something unless you live it. Right? The truth of God has to be lived to really be comprehended, and the Hebrew sense of understanding is much deeper than a sort of abstracted sense of the Greeks. And so this actually, I maintain, and I don't have time to go into this, but again, I could answer questions about it later. I think that the...
More time, Fred, maybe on Tuesday afternoon, so...
Yeah, I think that this is I see historically, and if you look at even someone has... Okay, well, even someone as hostile to Christian faith as Alfred North Whitehead, who wrote, Modern Science in the Modern World, recognizes that science wouldn't have been born had it not been for Christians. And part of it was this faith that's required to even do the start in the first place. Because there are many great civilizations where they didn't have science, and it's because it just didn't make sense to them to do it. It wasn't that they didn't have brilliant people or rich culture in many ways, but it takes a certain kind of faith to embark on this endeavor. And I think that just historically, not to mention the fact that in many other ways, this is just simply trying to cope with the revelation of God through the world around us. All right? But it's a picture of, it's a reflection, an analogy with how God reveals himself more concretely and specifically and intelligibly in his word. All right, so I have a list here, and again, maybe I'll save this for later if we have time, that basically there are tons of assumptions involved in doing science. A scientist doesn't go in there and say, well, let me assume nothing at all and try to make progress. He would get nowhere, all right? So a scientist goes in there and actually is saying, how many assumptions can I make? Please let me make more assumptions so my life will become simpler. And so, seriously, you know, if I have to include the moon's motion to understand my pendulum, you know, I'll be here all day. So you go in and you make tons of assumptions. Some of them are physical, some of them are metaphysical. All of them are important. And many of them are the cause of very deep reflection. And tomorrow I'll give a talk on the fine-tuning. And fine-tuning, there are two aspects of it in this book, which will be, there'll be a short, I guess, film clip about it, called The Privileged Planet. And there are aspects of this, namely, because what's being recognized there is not only that the universe is designed, but it's designed in such a way that not only is it designed, but we can actually learn about it. And this is astounded scientists throughout the history of science. When I was at Princeton, a very famous physicist there by the name of Eugene Wigner. And Wigner was much more open than most of the materialists. And I think I wouldn't even classify him as that. He was much more open to a theistic view of things. And he was astounded at, why does mathematics have anything to do with physics? You know, very little things like this, which everybody takes for granted now. He said, this is suspicious that it was set up for us. And he believed that was the most reasonable explanation, is that God had made it for us so we could understand it. And so, anyway, there are all kinds of assumptions which you need to do science, that you can separate things into small parts, that you can even do analysis and it all in any case and have something come out of it. And that things are structured in an intelligible way. You're often in physics looking for, and in any kind of scientific exploration, you don't even know what the question is. You don't even know what the language is that's appropriate to describe the question. And so a lot of the exploration has to do with trying to come up with a faithful language so that you can speak the truth about what you're looking at in the experiment. So, and then there's other things, and this requirement here I threw in here because this is, in our own day, is the big blockade of materialism, is that unless it's something that the people are willing to accept, they'll reject it. And the materialists simply reject a theistic explanation, so then that pretty much ends their discussion. But I think that the study of, for example, biology is going to confront people with it, whether they want to or not. Although I think you're confronted with it all the time. Okay, so anyway, so then maybe I'll save some of this for later, because I know but there's a whole cycle there. I can go all around the cycle, and it's an interesting reflection on. Now, one of the things that I think is important for me to state as a physicist, because so often, for example, if you read the popularizations of physics of Stephen Hawking or some of these other physicists, they will invariably use the idea that we go to fundamental physics to find the meaning of the universe. Right? That's how we're going to find out what it means, our existence means. Now, actually, this, I think, just going back to what I said about the kinds of structure in the universe, is clearly misses the point. Because what you have in nature, of course, you have all kinds of structure. And the kind of structure that we observe in physics is what I would call elemental structure. Right? The nature of the structure of, for example, the strong nuclear force is highly structured. Right? It's what holds nucleons together. But to say that now, we say the building blocks of nature are A, B, C, D, F, G, and we line them up like this, we found all the building blocks of language. Now, is this going to tell you the meaning of everything that's been written? Of course not. These are the elements, all right? So it's an elemental understanding. Of course, it's important to have an understanding of these elements so that you can write things, right? If you didn't understand the structure of these things, you wouldn't be able to write anything. But on the other hand, just denumerating this structure is not going to get you to the fundamental meaning. So the fundamental meaning is not found on the lowest level of order and disorder and of the structure of forces, right? Because forces are highly structured. But it's found on the level of things which are not governed simply by energy and geometry. All right? That's where you actually, for example, in biology, one of the reasons you can make so many different kinds, there are so many different kinds of organism is, you can write whatever you want. Energy, the energy of the different ways you can put together DNA and say different messages, they are, from the energy point of view, what the physicists would call degenerate. In other words, they all have the same energy. And so energy doesn't tell you what you should write. That's why you're free to write so many things with it. That's why DNA is such a wonderful piece of blank paper that you can write on, because it doesn't force you to write anything. And so then, therefore, what you do find, if it's structured, energy couldn't do it because it was powerless to do it. That's the whole thing that made it possible to write so many different things. Okay, so the meaning of things is not to be found in elementary particles. Even though I think that it's very interesting and it's interesting infrastructural knowledge, it doesn't tell you. So there are limitations. If you go through all the assumptions, and there are many assumptions to the operation of science, the inseparability, intelligibility, the operation of this cyclic method where you go back and test, there are some things which are always going to slip through your fingers, all right? And that is because science has limits. And the reason there's this big conflict between, supposedly, science, well, certainly science as it's defined by materialism and intelligent design, is the materialists assume there are no limits to science. That, yes, we should separate science and theology. Science deals with reality. Religion deals with fancy, fairy tale. And so, of course, then they rule out the existence of anything that isn't captured by scientific method. But, of course, the problem is then they rule out all meaning and their own brains, in fact, they rule out, right? So there are certain things, like, for example, ancient Egyptian hieroglyphics, right? No physical experiment, certainly not physical experiments on the nature of rock, would tell you what they meant, right? Because even though they're written on stone, say, if you understand the chemical bonds in the stone, that's not going to tell you what they mean. In fact, only if you met an Egyptian, you could have an interaction with the author to explain it. Then you suddenly realize these things are not random marks on this stone. They actually have some meaning. They have a detachable pattern. And so you need a Rosetta Stone to really penetrate encoded information. And so that is this existence of the detachable pattern means that science in itself, in the absence, of these Rosetta Stones, if you will, cannot decipher a meaningful message. But of course, teleology and meaning are in fact necessary in the whole operation of science. Scientists need to operate with metaphysics. And so without it, they can't do anything. So obviously now if we consider the possibility of extending science, which is in fact just being realistic about how science must function, then you're automatically confronted with, okay, we have to deal with teleology, then we need intelligent design as a way of functioning. And I already said this, the scientific method, I think, is a very good reflection of its exegetical method, Reformation exegetical method. And I think that it was no accident that someone like Faraday was doing this because he wanted to read faithfully nature. And he actually revolutionized, because see, what people were doing at the time, scientifically, would theologically be called eisegesis. A lot of scientists in Faraday's time would just have some fine-sounding idea, and they'd go and pluck data and prop up their theory. And Faraday would say, wait a minute, no. What you have to do is you have to let your experiment itself teach you what its content is, all right? And where was he getting that from? Well, that's how you do exegesis. You try to let the text speak to you. You don't go at the Bible with your own fine-sounding idea and then pick and choose verses to prop up your theology, right? He recognized that was not a faithful method, right? And so he recognized that you needed to read it from the nature itself. And actually, I would say Faraday achieved an accomplishment which has been unparalleled. He was mathematically untrained, and he actually unraveled the mechanism and the structure of the electromagnetic field, which anyone who has studied electromagnetism knows that is not trivial. And he also understood that fields are non-material, which I think was largely lost on people of his generation. But he thought it was actually his most important contribution, was the demolition of materialism. So, in fact, well, this is now getting into metaphysics, but the materialism really is based on an ancient philosophy of desiring control and of actually seeking to escape responsibility before God. If you go back and read, for example, Epicurus. But there are modern exponents of this, and also throughout the 19th century, which is where the materialists largely took control of official science. They were consciously, for example, John Tyndall, who was Faraday's successor at the Royal Institution, preached Epicurean philosophy when he addressed their equivalent of the National Academy there in his speech. It was in 1862. So really what we have is, in other words, in materialism you don't really have science versus faith. You have another religion. It's not Christianity versus science. It is Epicurean materialism versus Christianity. And we have to at least get to that point, and then we can actually have an important dialogue. Because the Epicureans have largely laid claim to science, but they don't possess it. They didn't invent it. And what they do actually does violence to science, in my opinion. So this is just from Epicurus. He's saying, look, we wouldn't even need science if we weren't worried about just trying to get rid of the idea of God. All right? And he's saying, you just don't, Jones, you can't believe that God did that. You just have to, the whole purpose for knowledge is to try to push the idea of God out of your mind. All right? This is from the Epicureans. But it's been revived in the 19th century, because in the 19th century there was a big revival of reading these ancient Greeks, and they were influenced by these ideas. But I think in the Enlightenment also they were. And it is a religion. If you look at Scientific American, all right, which is supposedly the premier journal of science communication in the United States. Michael Shermer is, in fact, a Christian man who used to have a column in Scientific American, okay, called The Amateur Scientist. A very wonderful fellow, Forrest Mims, he was thrown out of Scientific American because he's a Christian, not because he did anything wrong, but just the sheer fact they said it wouldn't look good to have a Christian because that's incompatible with science. Well, in fact, Mims, I think, did a much better job. Now here, of course, we'll put in what we call the skeptic column instead, right? So that we can free ourselves from theological talk. Okay, so here is, from May 2002, Michael Shermer's column, skeptic column in Scientific American. What does it say? God appeared at Caltech. Oh, I mean Stephen Hawking. And scientism is a worldview that encompasses natural explanations of all, eschews supernatural and paranormal, and embraces empiricism and reason as the twin pillars of philosophy of a life appropriate for the age of science. We show deference to our leaders, pay respect to our elders, and follow the dictates of our shamans. All right, so this is a pagan religion. And this being the age of science, we should worship scientists. This is our escape from theology by throwing out Forrest Mims and replacing it with the skeptic column. This is not science versus religion. This is another religion which has come in, right? I mean, it seems to me it's pretty obvious. And it was not even, it was explicitly admitted even during the 19th century. They called it the new religion. All right. So anyway, and of course, this is another famous quote from Richard Lewontin, who says, even if it doesn't make any sense, even if it does violence to biology, we don't care. We're going to believe it because we have a commitment to materialism. Moreover, materialism absolute, we can't let a divine foot in the door. We don't care, you know. And that's sort of, you know, if you remember Renault's quote, it was similar. So, I mean, I think that, you know, I don't obviously want to, you know, just throw stones at these guys. I think that what we should try to engage people in the discussion and to talk with people and to try, but I think that part of it is to having everyone come clean and say, look, I'm a Christian, here's where I'm coming from, this is what I believe, and what are you, you know, and where are you coming from? And the materialists, unfortunately, have not been, I mean, here, I think Richard Lewontin should be commended. He's being very honest. You know, I think this is wonderful. That's why I'm quoting him, because he's at least being honest, right? And he's telling you where he's coming from. And likewise, it's the people who say, no, we're just doing science, and you folks are doing irrational, you know, nonsense. well, that's just simply not a representation of what's going on. So, as a Christian, I think that it's important that we completely rethink science. All right? Now, there is a tremendous heritage of people like Maxwell and Faraday and others. There are a lot of people who've been thinking about this, and I'd say Christians really gave birth to modern science as we know it. And so it's not like we're starting from scratch, but I think that over the last 150 years, science has been basically taken hostage in many ways by materialist and Epicurean religious philosophy. And so we have to somehow rethink everything and see that we're making sense. I have a few examples here of some of my favorites, and I know I'm running out of time. Maxwell, again, he said, some people object to physical science thinking that it'll make you so you can't believe anything except for, the material. And he's saying, look, what I've endeavored to show, and this was in one of his introductory lectures to his students at, I think it was in Edinburgh, is that the particular function of physical science is to lead us to the confines of the incomprehensible. In other words, the study of science helps you appreciate all the more what God has done. And also, there's intellectual honesty. He said, look, this is what we know as Christians. You don't let things be willfully unexamined. Right? You put yourself to the test. Right? Then that's what Scripture says. Test everything. Hold to what is good, reject every form of evil. Right? So that's exactly what he's just saying. This is the rule of science as well. And so this is something I discovered. I had a collaboration in Marseille for a number of months, and I was in an old bookstore, and I found a book of poetry of Ampère, which most people didn't even know. In fact, a lot of the French scientists I was around didn't even know that Ampère had written any poetry. But this was an interesting, I translated this from French because it really impressed me. That Ampère, who was working on the early experiments on electricity, was very aware of the age of materialism in which he lived. All right, but anyway, he said, well, you can read it for yourself. But it's a statement. He just considered that when you look at when you study physics, you recognize that it's absurd to think this just happened for no reason. This is really the glory of God. And of course, you can see here he's making allusions here to one of my favorite psalms, Psalm 19, right? The heavens declare the glory of God, the skies proclaim the work of his hands. Day after day they pour forth speech. Night after night they display knowledge. There's no speech or language where their voice is not heard. Their voice goes out into all the earth, the words to the ends of the world. In the heavens he has pitched a tent for the sun, which is like a bridegroom coming forth from its pavilion, like a champion rejoicing to run his course. It rises at one end of the heavens and makes its circuit to the other. Nothing is hidden from his heat. The law of the Lord is perfect. Well, and that was not lost on the early scientists. Like I say, many of them were Christians, and it's been taken, I think, hostage by the materialists over the last 100 years. So, just a few comments. This openness means that science not only is open, it needs to be open. And there are a whole bunch of very interesting and important questions, like ethics. One of the biggest challenges facing the community of scientists now is bioethics. All this monkey business and manipulation, which is now possible, raises lots of ethical questions. The scientific community is largely powerless to deal with them because within materialism, the only ethical system is hedonism. It's the only system there's been since Epicurus. And hedonism, which has kind of morphed through history into various other, allied forms, leaves you basically powerless to say what you should do and shouldn't do, other than trying to measure people in terms of their gross national product, in terms of money or something like this to get a quantity. And they're all degenerating and dehumanizing forms of ethics. And so the Christian, I think, is challenged to be able to have a voice and say what is good and what is not good, right? And to think through what are very difficult and complex questions facing the scientific community at this time. And I think it's an opportunity for Christians to come forward and be helpful. But also, I've raised the point that accurate physical description is not the same thing as an explanation. And materials like Steven Weinberg is a very angry man. He's a very atheistic man in the sense of he explicitly and openly is at war with God. And he's a Nobel Prize-winning physicist and is making the life of people like myself difficult because he's trying to introduce rules in the American Physical Society which would make me illegitimate as a scientist because I'm a Christian, right? which is, which would then, of course, I will go with the great company of people like Maxwell and Faraday. They'll have to throw us all out. All right. But he just says, look, the more the universe seems comprehensible, the more it seems pointless. Well, for him, comprehensible meant reduced to a differential equation. Well, yes. If you reduce everything to a differential equation, you'll say it seems pointless. Right? Of course it's going to happen. But it's amazing to me he doesn't see that, of course, that had to happen in his own system. And it's an ethically demanding process. I mentioned this openness. In science, we have to do lots of things which are ethically demanding. Right? Refereeing, evaluation, recognition, mentoring, advocacy. All these things we have to do, whether we want to or not. And scientists need to be equipped. And as Christians, I think we have a very big responsibility to come in equipped with what would God have me respond to all these challenges which are there. Well, I've tried to just situate, in other words, intelligent design in two specific cases, the idea of specified complexity, which has the idea of a detachable pattern, and to show that, in fact, I think the design inference applies to science itself, all right, let alone to the more everyday details of looking at specific artifacts and trying to determine whether they were made by an intelligence or not. But the whole enterprise of science itself is, in some sense, I think, a design inference. And so I think there are all kinds of levels on which this kind of design inference thinking can take place. And I think it would be interesting to explore them, both for philosophers to think about it and also for scientists to think about it. Because I don't think that science can operate without metaphysical. All the scientists who've made big contributions were highly metaphysical. And I have other quotes of Maxwell who affirms this, but I think you just maybe can take it that that's... If you're going to get outside the box, you have to think metaphysically. And that's where big advances are made in science, when you think outside the box. Right? All right. And so tomorrow, again, I'll talk a little bit about Gonzalez's work and some other things on fine-tuning. But I'll stop here.
Thank you. So we've tried your patience and the endurance of your backside. That's how it's scheduled by the conference organizers. So we still have 15 minutes until this session is officially over. I want to emphasize again that what we have here in this network is kind of like a buffet dinner or a smorgasbord where these are ideas being presented that you are invited to sit and sort according to your own scientific understanding and to find apologetic material, apologetic tools that you can use in your context, both for your own satisfaction and to help others understand that there is a God. And I mean, that's what apologetics is. It's about helping others understand the truth of the Christian worldview. I wish we had a longer talk on the way in which Christianity gave rise to science. Because far from being a superstition and heathen science, it was exactly Christianity and the Bible that laid the foundation by which we do science, including the desacralization of nature and a bunch of other things. So there's a good book on that by a physicist named Stephen Barr, Notre Dame Press. I forget the exact title. I can give it to you if you're interested. And if any of you are interested in that Buechner article that Fred mentioned, I have it on my CD there, and we can copy it to the computer. We can get it on site.
This is his article on the amazing usefulness of mathematics?
It's a Word document.
Okay.
It's a computer character recognition thing. I'd like to use the last few minutes to have people ask questions of both Paul and Fred. So I'm going to just ask you guys to both get up or sit in the front or whatever you want to do and just shoot questions at them.
Yeah. Maybe it would be good if you, then you can say who would the question you want to direct the question to.
It's for you. And I was a little bit caught up in Dembski's explanation of the no lunch thing that he said. He said something to the effect, I'm not quite sure if I captured that, specify that if you experience a decreased amount of entropy, that's basically an inference to intelligent design or design.
No, no, that's not.
I misunderstood something.
No, I mean there is a information as it is defined within information theory, all right, can be thought of as an antithesis to entropy. And of course, in open systems, and this is the usual argument, people say, well, the second law has nothing to do with the origin of life, because obviously the universe is very far from thermal equilibrium, which is true, but which in itself is an interesting question. Why? But anyway, the universe is that way, therefore it's open system, therefore you can have entropy locally decreasing as long as it's increasing somewhere else. And so that in itself, it has to do just simply with the statistical fluctuations of things occupying the states available to them, and it could be totally random. So in order to understand Dembski's theorem, that was my slide there showing that really, and this is, I think, really my take on Dembski's theorem, is that what he is saying is that design involves an inference, or it involves a correspondence between the written message, be it in a cell or whatever, and a detachable pattern, which is a kind of theoretical entity. Right? It's a metaphysical thing. It's a pattern, but it's a teleological thing usually. It's a purpose. For example, the cell has molecules which are involved in its being able to move. And you say, all right, that is detachable. There's a function here, being able to move. Not just having lots of complicated molecules, but that enables the thing to move from A to B. That functionality can only be destroyed by coupling to a thermodynamic heat bath, which will just tend to randomize things and which will not teach you how to achieve the function. It'll just destroy the functionality. And so what he's saying is that, yes, that not only is the second law something you have to think about in terms of the flow of energy, but of course cells don't violate this second law because they operate, that you can study how they operate in line with energy flow given by temperature differences. But what he's trying to get at is there's something else going on here. They have functions. They have instructions for how to build things and how to do things. And those things are different kind of information because they're information which is specified, all right, to achieve a goal. And that will be lost and not gained through interaction with the heat bath. You see what I'm saying?